Now we get to talk about a topologist's bread and butter, namely quotient spaces. They can be a bit intimidating at first, but they are absolutely beautiful once you understand them. So the first definition is the definition of what's called a quotient map. So a function, we're calling it Q for quotient, from a topological space X to a topological space Y, is called a quotient map if this if and only if statement here is satisfied. Namely that given any open set in your codomain, its preimage is open in the domain. And vice versa. Given some preimage that's open in X, the set that you were taking the preimage of must be open in Y. Okay, so I'll just say here, sets open in X, if and only if, sorry, I meant to write Y here, sets open in Y, if and only if preimage open in X, is really what that is saying. Okay, so for an example, you might consider the quotient map taking this interval, which is half closed, half open, from 0 to 1 as a subset of the real line. And when I say subset of the real line, I'm thinking Euclidean topology. And you could think about some function Q, mapping that onto the circle. Sometimes we write the circle S1, and we're actually thinking about it as the set of points distance 1 from the origin in R2, again with the subspace topology on R2. So what kind of map could you do? Well, you could imagine bending this thing. So you're taking the interval and you bend it a little, so it looks like a smiley face, and then you bend it some more, so it looks like this, and then you bend it so much, and perhaps I should have drawn it a little differently, perhaps, bend it like that. So the closed part of the interval is on top, and then eventually I just close these two together. And so I'm sitting here, there's the closed half of my interval, there's the open half. This gives me a quotient map. Why? Well, I mentioned the main condition you have to satisfy is that sets are open in Y if and only if their preimages are open in X. But I kind of skirted over the fact that you also have to be a continuous map, which this is. It's a continuous map because for any pair of points you take, let's use a red marker. For any pair of points I take here, over here, right, if I took those 2 points, no, I was doing it right. Apologies. If I start with 2 points close together in the domain, they'll map close together, maybe here and here in the codomain. There's no tearing happening, right? I'm just bending a circle onto itself, or bending a line onto a circle. So it is continuous. And you can also say it's surjective. Right? Every point on the circle gets hit. In particular, this point gets hit by this point. So 0 maps to that connection point. And by this point, you're probably thinking, okay, what is this map? Well, you can actually define it if you want to. So given a point X in this interval, this map can be written as e to the 2 pi I times X. Right? And then what do you know? Q of 0 is e to the 0, which is 1. And I wrote this was R2, but you could just as easily think about it as the complex plane. And in that case, this is the point 1 in the complex plane. 1, or if you want to write it as 1, 0, feel free. 1 plus 0 I, however you want to think of it. Similarly, Q of like 0.999, can't plug in 1, but I can plug in stuff really close to it. would give me some point really, really close to 1 as well. So it's like really close to 1, but not exactly equal. But anyway, you get all the points you want. You fill out the entire circle. So it's a surjective map, it's a continuous map, and it has the all-important property that if you consider open sets in the codomain, their preimages are open in the domain. For example, if I took this set, imagine it as like an open chunk of that circle, the preimage would look something like this. It would be like that, open interval in there, right? Just imagine unfolding the circle and seeing where that highlighted interval goes. It would go somewhere close to there. Similarly, this interval down here might map to here or something. And the more important thing to consider, which you may have wondered, is what happens if I look at an interval containing this join point, right? Well, undoing that, looking at the preimage, would kind of split this circle. And so I'd have 1/2 of my interval here, 1/2 of my interval here. And then the question is, let's actually draw this in red. So maybe it's, this, and then it kind of teleports over here. Oops. Maybe that's the preimage of the highlighted arc of that circle. Is that an open set? And the answer is yes. You might think like, ooh, what about this? Right? Doesn't that prevent it from being open? But you have to remember, we're thinking about this interval with the subspace topology. So this is actually an open interval relative to I. It's a relatively open set because you could write it as the intersection of an open set with I. So it is relatively open, that's what matters. Both of these spaces have the subspace topology, so it works out. And similarly, if you go in reverse, right? So this is an if and only if statement. You can go either direction, but yes, the story is the same. The pictures would be roughly the same. That if I took a preimage of a set and it happened to be open in X, the corresponding set would be open in Y. So this turns out to be a quotient map, and it's sort of the quintessential example of a quotient map given in a topology course. But more often than not, we won't talk just about quotient maps. We'll talk about quotient topologies and quotient spaces. And so let's introduce a new definition. That if you're given a topological space, and now instead of thinking about Y as a topological space, we'll just think about it as a set with no inherent topology, at least not yet. And we're given a surjective map, which instructively I'm labeling Q, because you're going to think about it as a quotient map. Then you can define a topology on Y. So I'm calling it tau sub Q because it's the topology associated with this map Q. And I'm defining it as the collection of all subsets in our codomain whose preimage is open in the domain. So super similar to what we had back here, this whole statement, very similar looking. When you do this, the set or the collection tau sub Q is called the quotient topology on Y. And the quotient topology has a number of nice properties, but mostly we'll just work through some nice visual examples and see how this works out. So what you can say then is that looking back at this example, let me erase my red set and my highlighted set. what you can say is that the open sets in Y, so now I'm thinking about this as Y, the circle is my codomain, and originally I didn't have a topology defined on it, but now I'm thinking the topology is sort of inherited from the function Q and the topology on my domain. So what that ends up looking like is, well, a set is open in Y if its preimage is open in X. So you get the exact same sort of thing, right? This will be an open interval when I pull it back to the domain. So it's an open set considered as a subset of Y. And similarly, even if I looked at something like this, that would be an open set in our codomain because its preimage was an open set in the domain. So quotient maps and quotient topologies go hand in hand. Okay, so I'll be the first to admit that these definitions are a little bit unwieldy, and it's especially difficult to see how they might be applied or how they're useful or interesting. And I encourage you to sit down and try to think through these definitions and think why each of these conditions is important. Why does it have to be continuous? Why does it have to be surjective? If you leave either one of those out, do you have a problem? What other kind of definitions could you come up with for mapping one space into another in a nice way? And after some thought, and hopefully after seeing the examples I'm about to show, you would realize this is actually the most natural definition you can come up with. And similarly, the quotient topology definition here is the most natural definition you can come up with for putting a topology on a set, which is sort of a deformation of another topological space, right? Because that's really what we were doing here. We were taking an existing topological space and deforming it in such a way to make something new. And yeah, it really only makes sense to define these sets to be open. Doing anything else kind of misses the mark, because you want a nice continuous function, right? Topologists are concerned with continuity. They don't care about things that tear spaces apart. They care about things that preserve nice structural properties of your topology. So anyway, with that, we'll see a new definition. I'll say partially new. It's another way of defining a quotient topology. Some people prefer to think of this as like the essential definition of a quotient topology. Some people prefer using the previous one. They both work. I like this one personally. I like it because it deals with equivalence relations, and equivalence relations make sort of visual sense to me. So the idea is that if you're given a topological space, which we're calling X, and you're given some equivalence relation, which will be represented with a tilde, then you can always define the set of all equivalence classes, noted X quotient tilde, where this X bar is an equivalence class. And as you hopefully recall from a set theory class or wherever you learned about equivalence classes, an equivalence class is just the set of all points Y that are equivalent to your representative X. Okay, so kind of hard to represent that geometrically yet, but we'll see some examples soon. By the way, this isn't a topological notion at all. It's just a set theory notion. The way we introduce topology to it is we define a function. So this function we'll call Q sub tilde. The sub tilde meaning it's dependent on the equivalence relation you define. And Q because it's going to be a quotient map. And you just do the natural thing. You send every point in X to its equivalence class. Okay, this won't necessarily be an injective map unless you're equivalence relation is like the identity map or something really simple, more than likely you'll have multiple points mapping to the same equivalence class is what I'm saying. So not injective, but it will be surjective by definition. And if you define the quotient topology on it, so here I'm calling it tau sub this function, just as above. So just say, the open sets in X quotient tilde, quotient space, are those sets whose preimages are open in X. So define it as you would above. Then this function is called, sorry. Okay, as I was saying, this map, Q sub tilde, is called the natural map. It's not a term that's used all that often in my experience, but there you go. It's the natural map because it's the natural thing to do, send every point to its equivalence class. And X mod tilde, or X quotient tilde, equipped with this topology is called the quotient space. It is a topological space, and it's built from a quotient map, so we call it the quotient space. Okay, that's a mouthful. Let's see some examples. So one of the nicest examples is if we're working with a square, and these squares are going to be identified, or parts of the square is going to be identified in the following way. So let me draw this in yellow to highlight it. This bottom edge and this top edge are going to be identified. And what I mean by that is I'm going to glue them together. That's what quotient maps really do. That's how you build quotient spaces, is you glue parts of your domain together. And so I'm going to glue that edge to that edge. Let's forget about this donut I've drawn on the right and just show that intermediary step first. Gluing those edges together will give me something that looks like this. That's fine. So I'm gluing the edges, and let's say this was the edge. So it's kind of like I took a sheet of paper, I rolled it up into a cylinder and taped the edges together, right? So this edge and this edge became identified, means they map to the same edge on this cylinder. Okay. Next step you want to take is identify the opposite edges. So I'll put 2 arrows to just distinguish that they're unrelated to the first 2 arrows I drew. So any side with a double arrow gets glued together as well. So let's look at that here. That would be something like this. I guess the arrows would point this way after folding. Is that right? That depends. Yeah, they go this way. My bad. So my arrows would look like that, right? If I folded up that sheet of paper, but it had double arrows drawn on the left and right hand side. And what I want to do is glue now these 2 circles together. So you imagine taking this tube, bringing it around until it connects on itself. And exactly what you get is this donut, right? So this circle here is exactly this line with the single arrow that joins up and becomes a circle. Just keep that there. And this circle is exactly the double arrow circle that we joined together. Let me think for a second about which direction the arrows are pointing. I think now they'd be pointing this way if I'm drawing them on the top. Anyway, doesn't matter too much. But yes, this is how you can take a sheet of paper or a sheet of rubber or whatever you want to think about it as, and deform it into a torus, right? A donut, or the surface of a donut. It's like an inner tube filled with air. Now this quotient map is a little weird to write down if you were like working in Euclidean space or something, but you can write it, if you wanted to, as just sort of the natural map here, where you're saying, okay, any points here become identified here. And the way you could write it is you could be like, okay, well, if I pick a point here, let's call this x comma y, then it has to get identified with its pair right here, just x comma y prime maybe. So same x value, different y value. And similarly, you know, these two points get identified. And on the left and right hand side, these 2 points get identified. Maybe that's x, z, and x prime z, just because I already used y. I guess I should have used something other than x as well. But anyway, hopefully you get the picture. You can write down a map, or write down a equivalence relation that says the point xy is equivalent to the point, maybe I'll use zw, if and only if they have the same x coordinate and their y coordinates are on the border, or they have the same y coordinates and their x coordinates are on opposite borders. Right, so blah. We don't have to be super precise. You're just linking points together. Then anywhere else that's not on the border just gets identified with itself. You need that to ensure reflexivity of the equivalence relation. But yeah, any point not on the border is sort of in its own lonely equivalence class. Okay, and then this over here, the torus, is what we call the quotient space under that natural map. And the quotient space has some nice properties. So let me go ahead and erase these points so I have some room to draw. Cool. So you might wonder, what are the open sets on the torus? Well, you could imagine, you know, cutting out some little disk here, and okay, we want that to be open, but to test if it's open, you have to look at its preimage under this map. And so the preimage, I hope I get this right. Let's go back to the intermediary cylinder here. That would be sort of like, I guess, a little disk right here. And then if I unraveled it even further, okay, so I went one step back, now I want to go back to the square. So unraveling it even further, that would put it, I suppose, down in this corner, maybe. And so the question is this open in X? And the answer is yes, right? If you're equipping this square with, say, the Euclidean topology in R2 or something, then yeah, that looks like an open set. So great. Similarly, let's use teal or something. You might wonder what happens if you take some set here that happens to cross over one of the cut points, right? Well, okay, that would end up being like here, still crossing this horizontal line, and then pulling it back, it's going to have to unravel the cylinder into a flat piece of paper, and that's going to split it in two, right? So if you imagine doing that, what you would get is half of it would be up here, half of it would be up here. And the question is that open? And fortunately, the answer is yes. In the subspace topology on X, it is open. Right. I know it looks closed on this part, but it's open because it's the intersection of some open set in R2 with our square. Okay, and then similarly, what would happen if you did something like something extra crazy, like putting some set right at the place where all the corners come together? Well, that would look pretty weird. It would look, even in the cylinder, it would be split, but still crossing over the horizontal yellow line. And then after unraveling it, each of those halves splits again, and I would get something like this. By the way, notice the red is close to this half of the purple, just like in all the drawings. The upper half of the teal is close to this quarter, just like this. Is that the right one? I think that should have been that one, if I'm thinking about folding it. Anyway, and just like that. And similarly, the upper half here, teal is close to purple. That's this half, which is also this half. So you can kind of track the changes that have been made along the way. And then question, is the purple set open? Yeah, it's the intersection of 4 open sets in R2 with the square. So it's a relatively open subset of our domain, meaning, sure, yeah, this is open in the quotient topology on the torus. Okay, that's sort of a wild ride. Hopefully the pictures make sense, even if the definitions don't. And that's how you define quotient spaces. Next question you might ask is, what if I had a particular equivalence relation that's like fairly simple, and say my equivalence relation is defined as 2 points are equivalent if they're in the same subspace of my topological space. Okay, so I have a topological space X, I have a subspace A, and I'm identifying all the points in A to make them the same point. Remember, identifying means either gluing or just thinking of them as the same thing. So what we have here is a fairly nice equivalence relation. I have to give this as a condition because every point needs to be related to itself to be reflexive, but fairly simple equivalence relation. And this gives rise to a natural quotient map. Right? Whenever we define an equivalence relation, you can define some natural map that gives you a quotient space, just like we saw above. In this case, instead of writing it X mod tilde, sometimes it's more often written X mod A, where A is the subspace that's getting kind of crunched to a point. Sometimes it's also written X sub A. And depending on what terminology you use, sometimes people call this an adjunction space. Sometimes that means a slightly different thing. Anyway, it doesn't matter what you call it, the picture is this. You started with some topological space X, you had some subspace A. Remember, when I say subspace, I mean it has the subspace topology. It's not just a subset, it has its own relative topology. And applying this natural map that we get from the equivalence relation, you can sort of imagine it like taking a napkin and like bunching up the center. Okay, so you can think of the sides pulling in if you want. You don't really have to. Topologists don't care so much about shape. So I could have drawn this thing on the right as a square still. The important thing is that everything in A gets identified to a single point. Okay, so how is that useful? Right, we're just shrinking some subspace to a point, who cares? It's useful because you can do really interesting things. You can take a disk. So here I've labeled X as D2, meaning the disk in 2 dimensions. So it's a solid disk, and we'll say it has boundary. So solid disk with boundary. And in yellow, I've drawn its boundary, right? So I wrote delta x, meaning the boundary of the set X, the boundary of the disk. But you can also see that the boundary is a circle, right? So I also wrote it as S1. Whatever you prefer to see it as, they're all sort of homeomorphic to each other. And again, you can imagine this as existing in R2 if you want. That's typically how we represent the circle, the unit circle, S1. But the important thing is I have a solid disk, and I'm looking at its boundary and saying, okay, I want to form the adjunction space where I take that boundary and I shrink it to a single point. So let's see what happens if we just make it a little smaller. Well, I'm trying to shrink it to a single point. Spoilers, it turns into a sphere, but in order to get there, okay, you're shrinking, you're shrinking, you're shrinking. And the rest of the space kind of gets dragged along. Draw it like this. And let's add some lines of curvature to make it look nice. Do some more of those. Sure, good enough. So it turns into like a little basket, right? Because I'm just trying to shrink everything to a point, and I can't shrink through the blue area, so I'm trying to shrink around it. And then you go even further, and you start just compressing this thing, this yellow ring, until it's a single point. That gets you here. Right, and once you've done that, you get the surface of a sphere. Sometimes we call that S2. But you also could think about this as the adjunction space, right? It's X mod A. You're identifying everything in A, and there you go. Now, to be technical, I really just wrote they're homeomorphic here. That's my symbol for homeomorphic. To be technical, really, when you apply this map, all that's happening is you're saying, okay, I have my disk, and now I'm not worrying about the boundary. And the boundary itself right here gets identified to a single point. Maybe call it A star or something. Right, that's what my equivalence relation is. Every point on the interior stays where it is. Every point on the boundary gets condensed to a single point. So like really, this map is just doing this. It's just leaving the points on the inside unchanged, and then shrinking the circle to a point. But it turns out to be homeomorphic to the sphere. And what I mean by that is, well, the topology is the same, right? If you look at the topology here and you ask, what sets are open up in this space? It turns out to be the same sort of sets that are open here. Okay, so the open sets are preserved. That's what homeomorphisms do. It's just that the usual topology on a sphere is you're usually thinking of it as a subset of R3. And so you have a certain Euclidean subspace topology there. Whereas here, you're actually thinking of the quotient topology, and you're saying, okay, this guy is an open set because it pulls back to an open set here. The point together with, like, I don't know, the rim of the circle or something ends up being the rim of the circle here, plus its boundary, which is an open set in the subspace topology. And yeah, I mean, that also ends up being a nice set down here, right? If you look at that rim of the circle, it gives you a nice open set in R2, or R3, I need to say. R3 intersected with the sphere, at least. Because you imagine pulling that up, this boundary would have been this boundary, and that gets identified to a single, like, Arctic circle on the sphere. So you really do have, like, a nice relationship between open sets here, open sets here, and open sets here. So these two things work out to be homeomorphic, even though, you know, this one's technically X mod A, this one's technically S2. They are actually homeomorphic. It just takes some work to write down why. But usually when we think about this as topologists, we just go immediately from here to here. Think geometrically, the boundary of the circle gets condensed to a point, and there you go. Okay, so like I said, these things get fairly confusing, at least if you try to dig into the weeds and be really formal and rigorous about it. But at the very least, the important thing is to have this geometric and visual intuition for what's happening. Thanks for watching.